Good evening, everyone. Uh, let's start today's session. A second. Okay. Guru, is it visible for you, the slides, and I'm audible? Yeah, am I audible? Voice is proper?
So,
Yeah. Okay. Just please wait for some time. Then we'll start. Let's. Some other guys also will join. So, Dhruv, have you any questions you can ask? I think people will join a little late. So, we'll start our discussion now. So, Dhruv, is there any questions? Uh, Guru, I want to ask you whether you solved this assignment 9 or not, because the due date is over. I can't solve this live session like assignment 10 now because it is live now. So whether we can go to the assignment 9, that will be better for you. If you have any doubts, I can solve there. In this also I can solve, but you have to ask exactly what doubt you have. Okay. So yeah, I'll go to live session 9. In that assignment 9 is there. I'll save that one and I'll discuss about that. Okay. And we'll come to the this assignment 10 after that. Yeah. So I'm just sharing you the screen. Okay. So in live session 9, whatever the questions were there, I'll just solve one by one. Then you can understand. Uh,
I'm not able to audible.
uh, is it not audible now also?
So now it's okay.
Yeah. Okay. So I'll solve one by one questions of assignment 9 because that is not solved last time. And later we'll discuss about assignment 10 as well. Okay. Hi Nurul, welcome. First we'll solve this session 9, like assignment 9. Then we'll go toward the assignment 10 questions. Okay. So, okay. So here the question number first was in assignment 9, based on assertion reason. In that the assertion was PN photodiodes provide better responsivity without compromising fast response compared to PIN photodiodes. Reason they have given, the I reason is under the influence of diffusion and hence slow down the PIN photodiode response. So, may I ask you what you have given the answer in the last, like, during that assignment? Yeah, hi Anirudh. Can you tell me in the question number 1 what you have given the answer?
So both the assertion and reason are wrong.
Yes, both are wrong. Anirudh, are you agree with this point?
Right. Yes, sir.
Yeah. Yeah. So here the solution is like PIN photodiodes. PIN photodiodes will be having better responsivity Sorry, my handwriting. Like, responsibility compared to PN photodiode due to the addition of I layer between the PN junction. Then actually you have gone through I think this solution whatever it's given. Hi Suresh.
Anchor, everything is fine.
Yeah, everything is fine. I thought like assignment 10 we can't solve, so I was just discussing about this assignment 9 first.
No, no, I think your voice is feeble. I can't hear you.
Yeah, I'm telling like in assignment 10 we
Assignment
can't.
10. Okay. Okay.
Yeah, so I wanted to ask the doubts about that. So before
Uh,
that, I thought like assignment 9 I didn't solve that last time. So first
uh,
I'll solve the assignment 9 and I'll whether they have any doubt we can solve that. After that we
yeah,
can
yeah,
move
yeah.
to other.
Maybe I
Yeah.
have pen on paper right now.
Yes.
Maybe you just try to solve them. If they are having any questions, I will just no
Okay.
clarify. Clarify.
Yes. Yes.
Yes.
Okay. So Anirudh, if you have any doubt regarding this assignment 9, you can type as well as you can like you can say what the question you have any doubt like that. Okay.
I think
So
last
in
week Anirudh had one doubt actually.
yeah,
I think that
it
that is clear right currently.
did you got
Amit,
Uh, Hello, sir. Yes, I
yes,
think
yes.
I got that answer, but still that impact ionization, I'm trying to learn on. I'll let you know.
Oh, yeah, yeah, sure, sure, okay.
That concept gets clear. I think I'll get the concept.
Yeah, yeah. That one you understand, right? Why not n layer to the P side?
Yes, sir, yes, sir.
I
So,
think I had already cleared in the live session itself, right? That
yes, sir.
fact, the same thing
Is there
professor
any
also told me.
materials which has like where
Yeah.
holes has a higher impact ionization than like
Ionization
inside?
ratio, right, right,
Yeah.
right. Yeah,
So
yeah.
there they
Okay.
might use this sort of concept.
Yes, exactly.
Okay.
Yeah, yeah.
yeah. So in question number 2, can you let me know like what you have what you are thinking about this column A and column B? So short price means what? What could be the possibility in the column B? This text also you can text either you can tell. There are some options are there like electron flow inside the resistor, random arrival of electrons, thermally excited carrier under no light, inversely proportional to the load resistor, trans impedance amplifier. Is my audio is clear? Yes, my audio is
Ah,
clear.
yes, yeah, yeah. Your voice is clear, but a lot of noise is coming actually from your mic.
Okay. Uh,
I don't know why that the noise is like no. This is kind of thing. Yeah.
okay, okay, okay. I'm just try to fix it. I think it will be okay now. So guys, please let me know what could be the answer here. Like short noise, what do you think about this? Yeah. So yeah, option Q is the correct answer for this. Random array of electrons is like a shortness is due to this one. Okay. Then thermal noise. And S. Yeah, correct. What about this dark current? Thermal noise is like is due to electron flow inside the resistor, and it's also inversely proportional to the load resistance. Yeah, that's correct. The dark current is likely due to is corresponding to the thermally excited carrier current under no light condition. Okay, dark current. And the last one is obviously it will be T. Okay, so next question. Here, I think you have solved this one also. And this, uh, you have given the plot. Consider the plot below between the multiplication factor m versus electron ionization alpha E omega m in a silicon APD for different values of the ionization ratio K. Which of the following relations hold good for the given graph? Okay, so what do you think about this first one? The first one, okay? Yeah. And did you solve this one like according to that like video lecture? There are another condition also like m is equal to infinity or m is equal to 1. Option C and D also there. So did you solve this m? Elizabeth, have you solved this one?
Yes.
Yeah. So
Second.
what could be the m value here? If we keep the values of no, yeah. So is it kind of MSQ? So please let me know what other possibility of M also. Okay, you're right. Like option A is correct here. K1 is greater than K2 is greater than K3 and least is K4. Yeah, but M is going toward what? Like it is like is stopping somewhere or it is going somewhere. Like you can see the values M is coming from 1. Like in the y-axis you can see M is equal to 1, but it's going toward the if if K is you are keeping K is equal to 1, then what could be the M value here? K1 you are keeping 1. Okay, K is keeping 1. Yeah, third option. Yeah, you are correct indeed. If you'll keep this value in a multiplicative game, then you'll get the value like K1 is equal to 1, then that time M is equal to infinity. Okay, and K is equal to 0, then what could be the M value? Anyone? So for that you have to solve through this. Okay. Go through the video lecture, you will get professor's lecture. You'll find Ram, okay, and minus K. Okay. Ah. If you'll solve for K1 is equal to 1, then you'll get M is equal to infinity. But if you solve for K is equal to 0, you should find out the answer through this, okay? If you can calculate now, you can calculate and let me know. Okay, that's fourth question is, if the absorption coefficient of silicon is 0.05 micron per micron at 860 nanometer, then the penetration depth would be in micrometer. On upon alpha. Suresh,
Yes, Ankur.
yeah, in this K1 is equal to 0 if you'll keep, then how to solve this one? Like exponential is there, alpha omega. So it will be like 1 minus 1 upon E minus alpha omega m.
No, it's
Is it
actually
like,
see P equal to P naught multiplied with e power minus alpha square, right?
yeah,
Then P by P naught will be 1 by E, right?
yes, yes, yes.
Then if you equate 1 by E with e power minus alpha x, then alpha will be 1 by x.
Okay, okay, yeah, 1 by
Yeah, yes,
alpha.
sir.
Okay,
Yeah.
yeah. So Anirudh is correct. Right? Okay, so this question number 4 in this, the solution,
20 micron actually, I think.
yeah, it's 20 micron. That is all like this. Ex, y, p, e, 1 upon epsilon. And if you do this, then you'll get the value of 0.368. And alpha value you have given already, 0.05 micrometer inverse. In lambda also you have given 860 nanometer. So if you keep this px is equal to 3 m again 3 to the power alpha x. Okay, here you can get the value. If you keep all these values, this will divide and you'll keep here 0.3368 and alpha value, and you'll get the x value here, 20 micron. Okay. Got it this one? Anirudh, Kubro? Yeah. So next question is question number 5. The impact ionization coefficient for holes is greater than that of electrons in silicon. So what do you think about this one? Will you follow the lecture? What is the correct option for this? Yeah, correct. So the impact ionization coefficient for electron is greater than that of the holes in silicon. Okay, so it will be the false. Then question number 6 will go. Here, suppose an APD with a responsibility of R is equal to 10 A by W, okay, operates at a wavelength 1550 nanometer to achieve a quantum efficiency eta of 0.8 at its operating wavelength. The multiplicative gain has to be. So how we will calculate here? Uh, do you know answer of this? Okay, then yeah, correct. Guru. Yeah, so the solution, how we'll do this? Like lambda we have given 1550 nanometer. Okay, and we have given eta also 0.8. And R is 10 A by W. Now, if we calculate responsibility of APD, okay, APD is equal to M into eta lambda for 1.24. 1.24, if you keep nanometer, it will be 1240. Okay, nanometer will keep that. Then M will be 10 into 1240 upon 0.8 into 1.55. Okay, and then calculate, then you'll get answer 10. Okay, multiplicative gain will be 10. Then, okay, now the question number 7 will go. Here, this is MSQ question. We can see the square boxes. So the response time of a PIN photodiode depends on transit time and the RC time constant. What, which of the following would be the best way to design a PIN diode with a very less response time? So, what do you think about this? In this MSQ, which options are correct? Anirudh, Dhruv, let me know. Yeah, the RC time is constant and transit time is depending on the response time. Okay. Okay. Response time of PI and photodiode depends on the transit time. Okay, fourth one, decreasing the cross section area. Only one option, like uh, Suresh. Hello, are you there, Suresh? Okay, so thing is like here, this response time is depends on the transit time plus RC time part. Okay, so here the transit time will be like it will be like we have this RC time is constant. Okay, so only transit time. So transit time means how we can change the response time will be increased. So first one is like food. Still confused about it. First, I don't think so. If we'll increase the width of the eye region, then the transit time will be increased, I think. So response time will be increased because yeah, yes, okay. response time, okay, is equal to tau transit time, okay, plus RC. Now you know this is constant. Just a second. And this one we have to think like transit time. If width is increasing, then I reason width is increasing, then response time transit time will be increased. Okay, so that obviously it should be the second option. Okay, not a first option. Then another one is option D is there. By decreasing the cross section area, you are correct, Dubru. It's like cross section area will be decreased, then the transit time will be increase, and the response time will be increase.
Ankur, this I can take up.
Yes, sir.
So, so this is actually, guys, this is total response time of pin diode equal to it's an addition of transit time and the time constant. So, what is this time constant? Time constant is actually the capacitance and the resistance of the intrinsic layer. Okay, and the capacitance can be related to the diffusion depletion width also. Okay, I mean if you consider this transit time tau tr, the first term is actually width by drift velocity. Okay, the width of the intrinsic layer divided by drift velocity. So what happens if you increase the width actually? So if you increase the width, what happens? This transit time will actually increase, isn't it? So since transit time will be is equal to the W by drift velocity. So we need to decrease the width of the tau to get less transit time. Then what about tau RC? Tau RC is equal to time constant. It will be depending on the capacitance value. That is the capacitance equal to epsilon A by W. Okay, A is actually cross section of the capacitor, and W is again the intrinsic layer width. Here W and there W both are equal. Both are equal. So what happens here actually in the denominator W is coming, and here tau here W is coming in numerator. So what happens here if you increase the W, one term one tau TR is actually increasing and tau RC is actually decreasing. Okay, there is actually a trade-off between these two again here. So that is why if you think tau RC is actually a constant term, then tau TR can be reduced by decreasing the depletion width. The other way is if you feel like tau TR is actually a fixed and the width of the I region cannot be changed. So then in that case, tau RC can be controlled by using cross sectional area. Okay, that by decreasing the cross sectional area, tau RC can be reduced. But tau TR actually, if tau TR is for fixed W or fixed I region, tau TR is actually constant. So there are two ways to answer this question. If anybody asks you the best way, only one option, then it should be by decreasing the cross sectional area because width cannot be changed. So if they don't provide these insights, then you can actually opt for by decreasing the width, that also possible, and by decreasing the cross sectional area also possible. Yeah, it is the answer for that actually.
Thank you so much. Actually, I had also doubt in this question. That's why I was calling to you.
So you are calling? I didn't hear actually.
Yeah.
Hello, sir.
Yeah.
Yes, yes, Guru.
Sir, then the best way is decreasing the cross-sectional area only, no?
Exactly. So that
Then,
is why I'm saying if there is if it is mentioned very explicitly, like only the one possible way is best way is actually decrease the cross sectional area.
so the answer is only 4.
Need answer is only four, but this by decreasing the width also we can do that.
Yeah, I know that, but
Yeah, by decreasing the width also we can do that. See, if you decrease the width, tau TR also decreasing, and tau RC you are decreasing both, right? W you are decreasing and A also decreasing.
actually by decreasing, what do you say, width, then RC term will increase, no?
No, no, no. See, that is why I'm saying like decreasing. We are decreasing the area also, right? We are giving two options here.
Yeah.
If you decrease the cross sectional area and width both, then it should be like constant only. See, but you are correct. The best way is only decreasing the cross sectional area. So that is why we are giving half of marks for each of these. We are not making them wrong.
Yeah, that's yeah. Okay, guys, you have cleared this out.
Yes, sir.
Yes, we'll move toward the next question. Okay, so here, which of the following statement are about the available photodiodes? Right. So options are given here. Can you just quickly answer this? This is also MSQ question. So multiplication factor improves with reverse bias. And the second option is there like impact ionization coefficient for holes is higher than electron in indium gallium arsenide. 4 and 4. Yeah, you are correct only. And to construct the APD, an additional N layer is added to the N layer in a PNR. Impact ionization causes avalanche multiplication. Okay, so yeah, you are correct only. This option 1 and option 4 is correct here. Okay, so next question will move quickly toward the assignment 10 also. So next question is the response time of PIN photodiode is limited by drift
Ankur,
velocity. Yes,
Anirudh
yes,
was actually mentioning that the second option is still confusing.
yes, yes. First he told something. And the question number 7.
Question number 8, he was saying, I think.
No, no, for question number 7 he told actually.
Oh, question number 7. Okay, cleared. Okay,
Yes,
fine.
yes.
That's fine.
This width increasing and decreasing they had doubt. Okay. So we'll move toward the question number 9. Here the 9 is given like the response time of a PIN photodiode is limited by drift velocity, wavelength of light, diffusion velocity, photoelectron conversion. So here also quickly just answer this. Okay, well, but how you are telling that drift velocity? Guru? In question number 9 you are telling or 8 you are telling? Extremely different from the drift velocity. I think Suresh, you can give the better answer for this drift velocity and transit time. Suresh, are you there? Okay, let him just join first. I think he's no audible, guys. I think Suresh is not here around. I will wait for this one. We'll ask him this out better. He will explain properly. Okay. Okay. So question number 10 is that an APD with zero impact ionization ratio K is characterized by.
Can you hear me?
Yeah. Now you are audible. Actually, the thing
Yeah,
is like in question number 9,
right.
it's they are telling that drift velocity is uh,
Correct, correct.
limited.
I will clarify that. Can you go move forward to this next question? I will just clarify. I'm connecting my
Question
iPad.
number
Yeah.
question number 10 you are telling or 9?
Yeah, I will clarify question number 9. You just
Yeah, yeah. Okay, I'll move towards the next question.
yeah.
Okay. So here uh, in APD with zero impact ionization ratio is characterized by asymptotic gain, linear axis noise, asymptotic gain, asymptotic excess noise, exponential gain, asymptotic excess noise, linear gain, and linear excess noise. So here also please, okay, third one you already gave the answer, okay? Yeah. So here this ratio is 0, k is equal to 0, then multiplicative gain would be m is equal to e alpha e omega m, okay? So this question number 10 is correct here.
Guru, can you just allow me? I'm joining
Yeah,
from other
yeah,
account.
yes.
Yeah.
Yes, just a pause. I'll just complete this alpha e omega m. Yeah. This is the final while k is equal to 0. Yes. So you want to share your screen?
Yes, I will share my screen. Share my screen now. Yes. Can you see my screen?
No, it's not visible till now.
It's not visible.
And now it's, yeah,
Now it is visible.
yeah.
Yes. So the question is like in pin diode, the response time is limited by, right? See. So that's the question. So people are actually confusing with drift velocity and diffusion velocity. So now this is actually a pin diode. Okay. Now what is happening before discussing the pin diode, we were actually talking about P and photodiode. So this is P and N. Okay. Now this is actually a depletion region. Okay. Now what happens here before applying any bias to this PN junction, there is an inbuilt diffusion velocity because of the concentration gradient, diffusion of carriers across the junction leads to diffusion velocity. Okay, but what happens? Why we are actually applying the reverse bias? That will actually overcome this diffusion of the carriers, and it will actually try to carriers from one region to another region in a faster way. Okay, this we are actually calling it as a drift velocity. So this drift velocity is compensating the diffusion of the carriers here. So this is how we are managing the drift velocity by applying the reverse bias voltage to the pin to the PIN or PN junction photodiode. In this case, drift velocity is actually we are actually forming this drift velocity. We are applying reverse bias to the junction to get high electric field, isn't it? So that means we are actually creating high electric field in order to overcome the diffusion velocity which is already existing in the junction. Okay, this is already there in the junction. So we need to overcome this. Then only the carriers will move very fast, and they actually cross the junction and they will form recombinations and all. So similar thing it will apply for the pin diode also. In pin photodiode, diffusion velocity is already there. Okay, that diffusion of carriers actually limiting the speed of the pin diode because we need to apply more reverse bias to overcome this. We need to apply more reverse bias to overcome the existing diffusion process. So this we need to overcome by using high reverse bias. I think this one you would have actually already listened in first lecture. He was professor was talking about this. Without applying bias, also the carriers can move away. But due to the diffusion process, this is actually slower. That is why we are applying. We are going to applying a reverse bias. Reverse bias actually. Okay, that means diffusion process is getting slows down the response time of a photodiode, a pin photodiode actually, not the drift velocity. Drift velocity that is actually drift velocity is causing to move faster, the carriers to move faster. So is it clear?
I think it's clear for you guys.
Yeah. You need
I
to
think
remember
Anirudh,
what is the cause and what is the effect actually. So then you will understand. So if you say drift velocity, see, some people are actually saying what they are saying. See here, they are saying like drift velocity is equal to W by TR. Now they are what they are doing like TR equal to W by VDR. Okay. Now they are saying like drift velocity. If you increase the drift velocity, the response time will decrease, and if drift velocity decreases, then response time will increase. They are thinking like that, but this is not the correct way. See, VDR is actually the effect of the transit time of the carrier. Okay, so that is why we should when you write this equation this way, you are actually depending on VDR. TR is depending on VDR. No, that VDR drift velocity is always decided by the transit time of the carriers. Okay, this is already defined. Okay, now this drift velocity we are increasing by accelerating the carriers here. Okay, this relation is good. This relation is good by accelerating the carriers. Okay, this is external bias. Yeah, thank you.
thank you, Suresh, for explaining this one. Now we'll go to the another question. Is it okay for you guys? Is it understandable for you? Okay. So now we'll go for okay.
Before, can I leave or is there any more
Anirudh
question?
raised one
Yeah,
his
yeah. Please,
hand.
Anirudh.
Sir.
Like when they say it's limited, it can also be the higher limit. So if I see, like, there was one graph that sir showed where the velocity and E was compared, and after a certain point, the drift velocity is constant.
Saturated, yeah.
So could also mean drift velocity there.
See, why it is getting like that? The carriers attain the maximum velocity. Okay, further it cannot be increased. But how we are actually getting that drift velocity is getting saturated due to the external applied field, right? Applied electric field, applied bias. So that we are actually the drifting problem we are actually creating. That is a secondary process actually. The primary already diffusion is already taken place. That is what if diffusion is not there, even if you don't apply the reverse bias, the carriers will move more faster because there is no barrier at all, isn't it?
Okay, sir, but if you want more speed, then it is actually limited by the drift velocity. Like what the or the is
That
it called
way
like saturation velocity?
Yeah, exactly. I understand your question actually. When it is getting saturated means it, that is that the carriers having very fast rate. It is around 10 power 6 per meter per second like that. Okay. Uh, and if you wanted to go beyond that, I think that I don't know that is hypothetical for the carriers. They can't move with the velocity of light, right? Sometimes in the medium, since it is limited by the diffusion process that is already existing in depletion region. Yeah, I understand that. Yeah, that might be also possible. Like the drift velocity due to drift velocity that is limiting the speed. But the mainly the speed is not limited in terms of the drift, right? So that is what the catch here. The speed is increasing as we increase the electric field, reverse bias.
Yes, sir, but that then it hits a plateau, no, sir. It doesn't increase after a
Yeah,
certain
yeah,
point.
yeah. That is correct.
So then, in a way, it is a sort of an upper limit for the limit of speed. So they didn't mention in the question if it's a higher speed limit or a lower speed limit. So I
Okay.
thought it is the higher speed limit. What drift velocity?
Okay. So you mean like no, that's you are not actually looking into a prospect of slowing process here. You are actually looking in the prospect of where speed is where the
Yes.
speed is
That
too
from
high
that
and
perspective, yes.
in that perspective you are actually thinking right.
Perspective,
But the
yes,
question is actually like why this process is slower. When you don't apply when you apply very high very low electric field
yes, yes, I got it.
across the yeah. Okay, thank you.
Okay. So this question 9 is okay for you. Now question 10 also we have discussed. We'll move quickly toward the next question. We'll finish this one. Yeah. So here the instruction for question 11 and 12 is given. Suppose you are asked to design an indium gallium oxide PIN photodiode with a 3 dB frequency of 10 gigahertz while maintaining a responsivity of at least 0.85 A by like ampere by watt at 650 nanometer. Assume that the absorption coefficient is 10 to the power 6 per meter at 1650 nanometer, drift velocity of 10 to the power 6 meter per second, series resistance of 2 ohm, relative permittivity of 2.4, photoelectron conversion efficiency of zero point 0.9, and negligible phase shift reflectivity. So question number 11 is given have asked like the minimum width of the eye region is in micrometer. So did you solve this one? Right? It's a numerical and yes. Okay, Anubhav. So I'll just write
I
down
think they have
the
solved it. Yeah.
yeah 1.24.
To the
So
13th question, I think. Yeah.
yeah, and this transit time of the carrier is in second. You have to solve that also. Okay, I'll just write down here the equation of lambda upon 1.23, which should be in micrometer, and that that's a responsivity, and then after that quantum efficiency, eta should be 1 minus RF into uh, to 1 minus e to the power minus alpha minus. Okay, so that you can solve this omega value, you can take it out. That is minimum width. Okay, and this in transit time we have just now Suresh told that VDR drift velocity is equal to omega upon transit time. Okay, now okay. Like that you can solve this question. After that, the question number 13 is there. Assertion: the SNR can be improved in an APD if the multiplication factor M can be increased until the excess noise becomes comparable with thermal noise without affecting the overall noise. And reason given the short noise is much below the thermal noise when lower number of photons are incident on the detector. So here, just tell me what could be the answer here. First one, Lieutenant.
See,
Anirudh?
this question, if you wanted to answer, you can actually refer to the last lecture, that semiconductor photodetectors 4. There he explained the noise and all noises. The professor explained very well why if you know if short night is much below thermal noise when lower number of photons are incident on the detector, then the M can be increased until the excess noise becomes comparable with thermal noise without affecting overall noise actually. So this is actually the reason, and that's what the statement assertion.
We'll move toward the question assignment 10. In that, if you
Ankur,
have doubt,
anyhow, we are not going to discuss the
yeah,
answers
yeah,
right in
yes,
lesson. I can give
yes,
right.
yes.
Maybe
Just
next week I
we'll
can
just
come
start.
up. I can come and I can explain them.
Yeah,
Sir, I have a doubt in third question in assignment 9.
assignment
Assignment
9.
9.
Okay.
Yeah, can you
Okay.
please go to that, Ankur?
Yeah, yes, yes.
Yeah,
Yeah.
yeah, super. Yeah, this. What is the doubt? Can you just?
Sir, for K1 equal to 1, M equal to infinity, they are saying, but it's actually a curve now. It still depends upon alpha and width.
Uh-huh.
If they said that alpha means omega equal to 1 means they also provide that condition also, then M equal to infinity.
Uh, I don't understand. So your point is K1 equal to 1, M is equal to infinity. Is what you're saying?
Ah, yes, sir, third one.
Right. Third one, you are not agreeing with that.
Ah, yes, sir.
Why
They
you are not
also have
agreeing?
to provide.
I'm just seeing the curve.
Yes, sir. I
That
got
curve.
one
Ah,
in the lecture. Sir said that M equal to 1 by 1 minus alpha width.
see, K equal to 1, again alpha EWM is also 1.
So it's not they are not providing it now.
No, it is already provided in the x-axis, right? See?
So it's changing now. Means for 0 to 1 also it's changing.
Yeah, 0 to 1. See, 0 to 1, there is a curve. There is a M
Yes.
has a curve. It is not a straight line, right?
Yes, sir.
Yeah, it is a curve. Yeah, it has. But only it has a value of infinity at K1 equal to 1 when the alpha EWM is also 1.
But they are not provided that option in third option. Means
No, no,
It
third
is
option. See, alpha EWM is already there in x-axis. You can find out that dotted line is drawn for that only. Alpha EWM you have to find from the graph itself. Maybe you are confused with alpha EWM is not given. Is that the question?
actually it's an x-axis, no? In x-axis, every term
No, no, x-axis every
it's,
time cannot be taken. Actually,
sir,
I'm
x-axis means zero. It's taken from 0 to 1. They are drawn a curve.
curve. Yeah, that curve is actually going to infinity at k equal to one, k1 equal to one at some particular value of alpha E and WM.
It's curve only means in the graph. They have to specify that alpha and omega equal to 1. Then only option 3 will be correct.
See, alpha EWM. See, I understand your question, Duru. This alpha EWM. If you, why we have drawn the dotted line there? The dotted line EWM.
It's 1, sir.
It is one. So it is already given. It is one. Then what is going to be K1 in this case?
Hmm?
K1. What should be the K1 value?
K1 equal to 1.
Yeah, that you have found actually. And what is the M value in this case?
So m value is equal to 1 by r, 1 minus
No,
r
no, no, that will not be there. See, you have told me alpha EWM one and K1 is also one.
to
Then what
infinity.
will be M value? Yeah, that is also one of the possible option. I'm saying. I'm saying
Yes,
it is actually it is. I'm not saying like it is correct. It is also one of the possible option for you.
yes, sir. It's possible option.
Yeah, yeah.
So if they are, then they also provide alpha omega equal to 1 in the options.
No, why should we
To,
provide from the graph? You can find out, right? This is the
yes, you
graph they
can
have
find
given
it.
very clearly. Yeah.
okay. First, you see
Value that we
clearly,
are
then
K1.
like you can see x and y axis both together, and k also value is there. It is
See,
one k1.
if I don't draw the dot line, I would have mentioned that alpha EWM is also one. I have
Okay, sir.
explicitly drawn the dotted line so that you can observe the graph very carefully before answering the question.
Did you got Duru?
This is what my intention actually. Yeah.
Okay. Okay, guys.
So
So here we'll wind up today. If you have any doubts, you can ask in discussion forum, as well as I will just send you the link of form.
yeah.
Nobody is responding nowadays in the Google form I sent previously. Very few people has
Okay, okay,
responded.
Ankur. Bye. Bye,
Yeah.
Anirudh and do. If you have any
Thank you,
further question,
Suresh.
please
Yeah.
please actually send in the discussion forum so that professor also can see them, and if I don't have any answers, he can also reply when he gets time. Yeah. Okay.
Yeah. Thank you so much, Suresh, for joining.
Yeah.
Yeah. So, guys, here in sending the form link as well. You just ask your questions about this question number, like assignment 10, because we can't discuss now, it is live. Okay, guys. 1.24. What is that, Google? Can you clarify what is that? Okay, okay. Yeah. Something. Yeah, yeah. Okay, okay. Okay, Google. Okay, guys. We'll stop here now. We'll meet next week and we will discuss about this assignment 10. Okay. Doubts, please ask whatever doubt you have. We are free to uh, solve these doubts. Like we are very interested to get your questions. Okay. Professor also likes uh, to see doubts and regarding that lectures. You can criticize also. If you have any comments, also you can share in the discussion forum. Okay. Yeah. Thank you, Anirudh. Thank you for joining. We'll stop here the session now. If you have doubts about this week 10, you can just type in the chat box. I will keep for for some time. You can type questions about this assignment 10. Okay.